All right. I believe that I sent out the grades, right? Like overall, like how the class did. And did I say the average? Okay. I thought it was 81, but that was before the bonus, I believe. So it was a good average. I have a huge pile of stuff up here that I need to get back to everyone. I just keep on running out of time at the end of class, and yeah, I'll try and get that passed around today while you're taking your quiz at the end. All right, so we're going to start Power Series today. I asked you to watch a video on it. I printed out the notes. If you watch the video, here you go. These notes are not that different than what was out there, but I did make some modifications to it, and we're going to do different examples than what was in the lecture video. That's what I'm going to do today. But we'll talk through these notes. There we go. I also did post the solutions to the exam right there out there. Okay, let's talk about Power Series. So what we've got here, before we start, and I printed you the notes so you don't have to write all this down, all right? Before we even begin, I need to make sure everyone remembers what an absolute value means. So if we say the absolute value of x is less than a number c, then what we mean is that x is between negative c and positive c. So as an example, if I say the absolute value of x is less than 2, that means that x must be less than 2, but at the same time greater than negative 2. And we're going to need this pretty much the rest of the day, all right? So now we talk about a power series. A power series is a series of the form, this sum, c sub n, x to the n. How many of you watched the video? Most of you? Okay. So I'm kind of rehashing what I already talked about. It's just the sum of a bunch of powers of x, right? That's what we have, with constants in front of each power of x. Those constants may change or they may be the same, okay? It just depends on the actual power series we're looking at. But the x's should always follow a pattern that as you move out, the powers go up. Now they may skip, okay? You may start off with, no x, then an x squared, x cubed. You may have every power of x represented. But if some of these c's are zeros, then you could skip a power, right? So you could have like some number, no x term, an x squared term, no x cubed term, but then an x to the fourth. So that could happen also. All right? So x is our variable, c sub k are constants. If we fix an x value, then the power series may converge or diverge. So as soon as we assign a value to x, this just becomes a series that we've been studying. That's all it is. So we'll have to investigate for what values of x it's going to converge or diverge. Now there's a more general picture. Hold on just a second, so you know what's going on here. All right, so if x is a value for which it converges, then what we can do is we can define the power series as a function. Say this function f of x is defined to be this power series, as long as it's going to converge. Then for x's that you plug in, you have a value that comes out, so it's a function, right? So it's a well-defined function. The values of x for which the series converges is called the domain. So this is something we've talked about before, like what's the domain of a square root function, what's the domain of a log function, things like that. Well, now if we have a power series representation of a function, the domain is just the values of x for which it converges. Let me see here. Remember, f would then be, the function would then be an infinite sum of powers of x. In other words, an infinite polynomial. And then this very, very important example here. This is going to motivate a lot of what we do for the rest of this section. It's taking what we did back when we were talking about geometric series. So if I take this general power series and I say all my constants, all of them, are ones, right? And just let the powers of x increase, then I get 1 plus x squared plus x cubed, and it just continues forever. This is very similar to the geometric series, except that we need to see that the a is a 1 for all of these, and the r is the x. So if we replace our a with 1, we replace our r with x, we get this geometric series, which is a power series now, right? And we know that if the absolute value of r was less than 1, which for us now is absolute value of x is less than 1, it'll converge. If it's greater than or equal to 1, it diverges. All right, any questions on that? No? Okay. Now we can generalize this power series, making a small modification. In the previous power series, we just had x here. But if we put x minus a, what this does is it just shifts our power series. And so we call it the power series about a. So before, when we had x, it was really x minus 0. So the more general form would be x minus a. And again, we could look at all the terms and look at if, this is the most important one to start, what if x is a? If you get x is a, you get zeros there. So you're basically adding up an infinite string of zeros, which should give you, well, it converges. That's the most important thing. It should converge. We do have to take into consideration this first constant right here, because if we get 0 up there, this right here would become 0 to the 0, which is a 1. I put it in red here because this is a real iffy sort of thing. You remember how we defined 0 factorial to be 1? Well, for power series, if we let x be a, isn't this first one 0 to the 0? What's 0 to the 0? It's indeterminate if we're taking a limit, right? Like 1 divided by 0 is completely undefined, right? Now, if you get a limit where the numerator is going to 1 and denominator is going to 0, that's different. That's something you'd have to figure out in a limit. But strictly, the number 1 over the number 0 is undefined. What is 0 to the 0? It's kind of like one of those, it's kind of like the 0 factorial. We have to define it. And for power series, 0 to the 0 will be 1. If you want, I put it here in red because if you want any more clarification on that, it's going to require me showing you something in my office. I was talking to one of my colleagues about it, and we agreed to what the best way to show that to everyone if you want to see it. Okay, for now, though, because of time, we're just going to take it on kind of faith that this first piece right here will be a 1, which means the first term of this series will be c sub 0. So when we were saying it was a bunch of zeros adding up, it's all these would be zeros, but that first one would be c sub 0. Okay, times 1. Okay, so that's but the important thing is that it converges. So anytime you have a power series about a, if x is a, it converges. Yes? It should go to c sub 0. Yep. Now let's do some examples, all right? This is what really today is about. And what we're going to see from this is that when you're looking at a power series, it's going to really, the two things that are going to be most important are the ratio test, which we've seen, and then messing around with the absolute value like I did in the very beginning of class, showing you that what the absolute value of x being less than 2 or whatever represents. So here we go. Everyone jot this down. I'm going to copy this and go to a new page with it. Where's my copy? All right, so for what values of x does this series converge. Now, what I would recommend you get into the habit of doing is writing out what the first few terms are. Right, like plug in n equals 0, and then n is 1, and n is 2. Just maybe write out the first 3 or 4 terms. And the good part of that is that later on, you're going to be looking at a series and having to go, like the series of the terms, and having to go back to the summation notation. So it's good to kind of see it both directions. Does that make sense? Yeah. Yeah, we're just writing out this plus this plus this. So we're writing it out as a sum. So first few terms, question? Yeah, that's part of, that convention that we had that 0 factorial is 1. So let me plug in 0 first, okay? What do you get when you plug in 0 for n? You get 1 over, you get 1 x to the 0 over 0 factorial, right? I'll do the next one, then we'll simplify it. Plus, now we'll have n is 1. So what do you get? What's that? 3, right? 3 x to the first power over 1 factorial plus, now plug in 2 for n, 5 x squared over 2 factorial. Let's do one more. Now we're plugging in what? 3, 7 x to the third over 3 factorial plus ... That pattern continues. Which I could now say that's just the same as 1 plus 3x plus, what's 2 factorial? 2, so 5 halves x squared plus, what's 3 factorial? 6, so 7 6 x cubed plus ... Now again, this is just so that we get used to seeing a power series written out so that we kind of could go back from this, like try to recover what the summation notation of this power series is. The more we look at them, the better we get at it. All right? All right, so we haven't done anything to answer the question. We've just written out terms. Now let's try and figure out what it would take for this thing to converge. So we look at the series, we look at what's inside here, and we say what would make that converge. And we have all these different tests that we learned. We're going to use the ratio test. That's the one that usually works with these power series. And that's because we have x to the n. Anytime we had n up there, power series, ratio test always seemed to work out. So what I'll do now is take this down here and do ratio test. And the ratio test, I need to define what a sub n is. A sub n for us would be that 2n plus 1 x to the n. And then on the bottom, n factorial. What else do we need for ratio test? A sub n plus 1. I'll do that in a second. I'm just going to write out what the two things are. Now, as we move on, I'm not going to show all this detail. Initially, this first problem I will, but then I'll start to trim out pieces of this. A sub n plus 1 would be what we get when we plug n plus 1 in. So we get 2, and then here's my n plus 1. I noticed on the test some people had trouble with that. Plus 1. And then x to the, now I'm plugging in the n plus 1 there. And then all of that over n plus 1 factorial. Right? So I've replaced all my n's with n plus 1s. And now I just multiply this stuff out and clean up the a sub n plus 1. We will get, what's in that parentheses? 2n plus 3. And then I can rewrite x to the n plus 1 as x to the n times x. I can rewrite n factorial as what? Or sorry, n plus 1 factorial as what? N plus 1 times n factorial. I mean, we've done enough of this ratio test, I think, that we know where we're headed, right? So let's go ahead and clean it up to the point that now when we put it together, things will cancel nicely. So here comes the ratio test. I'll squeeze it in right here. Or you know what? Let me go to a new page. Everyone good up to this point? Okay, so for ratio tests, here's what we do. We take the limit, n goes to infinity, absolute value, a sub n plus 1 over a sub n. This is equal to the limit as n goes to infinity of absolute value. Now, on your test, I noticed this happening a lot also. A lot of you were dropping your absolute values, which was correct because the series that you were looking at was always positive. But with these power series, we need to keep those absolute values in there because we don't have control over x, right? N is a positive integer, but x can be anything. So we need to keep the absolute value the whole time. I just don't want you developing a bad habit. Yeah. Well, it's a variable in the sense that we don't know its value. Okay, we can assign a value to it, but it's not restricted to integers. Like n was always our index on our summation, so it was always like 0 or 1 or 2 or 3 or 4 or 5 integers. X can be a negative real number. It could be. So we don't have that restriction. Does that make sense?
Yes, because on the limit, it's a constant, right?
Well, the limit will only affect n. So whatever x is just sits there while n does its business. We'll see when we get to it. All right, so I'm going to plug in my a sub n plus 1. So that would be my 2n plus 3 x to the n times x all over n plus 1 times n factorial. Then when we divide by a sub n, it's the same as multiplying by the reciprocal. Again, you've done enough of these now. Do you feel like you've done enough of those? All right, I hope you do. 2n plus 1 on the bottom there, and then x to the n. So we get lots of nice cancellation here. We got our x to the n's are gone. We got our n factorials are gone. And so the only thing left is going to be our 2n plus 3, our x, on the bottom, n plus 1, and 2n plus 1. Right? Okay, so now what we'll do is we'll write out what remains still in the limit. Limit n goes to infinity of our 2n plus 3, and then we have our x on top over n plus 1, 2n plus 1. Close off the absolute value. Now this is where we're saying the n, right? The only things affected here are those n's. That x is independent of the n. So what we can do is really just figure out what happens to those three factors. And what does happen? I'll write it out. Limit n goes to infinity, absolute value, 2n plus 3 over, let's go ahead and expand out the denominator. What would you get if you multiply these two together? 2n squared, 3n plus 1. And then look at what I'm doing next to it, times absolute value of x. What? What, we? Oh. Well, he always says that? That's the first time I've ever heard you say that. Yeah. All right. All right, what happens to this, everyone? 0. Why? You could do L'Hopital. You could just divide everything by n squared, right? Again, that's something we've done so much now. We have two polynomials. Degree of the bottom is higher than the top, so we know that goes to 0, right? Now, the x, though, is still sitting out here. So what happens here in this limit is that we get this whole thing right here to go to 0 times the absolute value of x. So what's happening here is no matter what x is, no matter how I choose x, it's going to get killed off by that ratio in front of it. It's going to go to 0. So this whole thing is going to 0. Right? What do we need for convergence in the ratio test? So this goes back to, now, what is the conclusion from ratio test? If this limit, if this whole limit up here, if this thing right here, if it's less than 1, we have convergence. And it's going to be 0 always. Right? So it converges always. Now, how do we say that? Therefore, the series n equals 0 to infinity of 2n plus 1 x to the n over n factorial converges for all x. Now, that's one way to say it. Another way to say it is that it converges for all x element of the real numbers, right? So I'm giving you different options as to how to say this. You can say that. You can say that. You can say if x is an element of the interval negative infinity to infinity. Or you could say x greater than negative infinity, less than infinity. And the last one is the one that I usually will adhere to, only because later on, as we get problems where our answer is not everything, it's usually going to be like between two numbers, and we'll always write it in interval notation. So we may as well do it now. That's right, it's in terms of x. That's the important thing. This power series converges no matter what x you ever plug in. Now, I have a way of trying to visualize this. Let's see how this works out. I was a little bit hesitant to show this. Let me see here. Where is that guy? Yeah. Okay, can everyone see this? So here's my Mathematica. Remember we had our series written out. It was 1. We wrote out the first few terms, right? 1 plus. Okay, and what we said is that if you do that, right, forever, it will converge for any x we plug in. So if I plug in like x is 2, replace that x in that formula with 2, that, when you add that up forever, it will converge to a number. Yes? So I've had Mathematica, I wrote the code up for this to, I'm going to plug in a value of 2, okay? Everyone okay with that? Yes, okay. So if I plug in 2 right now, what would I get? Now I'm only looking at the first two terms. Remember, it's an infinite series, but I'm just looking at the first two terms. If I plug in 2 right here, I get 7, don't I? So let's go and let's add one more term to the series. If I add one more term, oh, hold on, I'm changing my x, not my terms. Here we go. There we go. So now here's our 5x squared, 5 halves x squared. Didn't we have that on there? If we add that up, plug in 2 there, we get 17. What we've concluded is that if I keep going out and adding more terms, I'm going to converge to a number. So now what I'm going to do is I'm going to drag my number of terms out and watch what happens to our sum, our nth partial sum. What should it do? What should it do? Converge to what? No, I don't know. Okay? What I do know is it converges, though. I don't know what to. Remember, we were never able to tell what it converged to, unless it was geometric or collapsing. But what I can promise you is that it should converge. So watch me drag these out. Now I'm starting to get lots of terms in my series. But look what's happened to my sum. Even as I drag out, well, crap, I've got a bunch in there. Let me zoom this back out. It's too zoomed in there. Look at all those terms, okay? Notice what's happening to my sum. Do you see that last number there? 36.945. Look as I go further, it's not changing, right? It's still changing, but it's way out here. Many, many decimal points down. So maybe I'm 20 decimal points down, I'm actually changing. But the first few I've got. So the further I go, the more accurate I get. But it converged, right? Do you see that? It's not bouncing around anywhere. Now if I back it up and I go back, there is a point here where it will start changing. So here we go. We had some changing, right? So I have 9 terms in the series. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, just forget that's the 9. I've got 10 out there, right? So Here it's 36.93. If I go a little bit further, it changes, and about right there is where I stop. I'm within, tenths, hundredths, thousandths, 100,000ths. I'm within 100,000, 1/100,000th of the actual convergence value. Yes or no? Now, if I change my x, will I still get convergence? Because I said if I plug 2 in, right? What if I change my x? Should I still get convergence? Okay, so let me change my x. I'm going to make it a negative number. Now, if I drag this out, watch what happens to my nth partial sum. Oh, hold on. Trying to get in here. See my convergence there? Okay. So our theoretical result from ratio test says no matter what x we pick, we should get convergence. All right? Now let's compare that to our next example. The next example we have, you have this on your sheet, right? For what values of x does sum n equals 1 to infinity 3x minus 4 to the n over n squared plus 1 converge? All right, so we write out the first few terms of this. And where does our index start here? 1. So let's write the first few terms. Yeah, first one, you plug in 1, we get 3x minus 4 to the first power over when we plug in 1, we get 2. Then I'm going to have 3x minus 4. I'm going to be squared over 6. Right? No. 5. And then 3x minus 4 cubed over 10 plus ... So again, that's just to give me an idea of what's going on. And now it's time to apply the ratio test. Now I'm going to move pretty quickly through this one because we've done it so many times. Ratio test means I need to take the limit, n goes to infinity, absolute value. All right, let's do a sub n plus 1. That would be 3x minus 4 to the n plus 1, but I'm going to go ahead and write that as 3x minus 4 to the 1 next to it, over n plus 1 squared plus 1 times, so this part right here is just my a sub n plus 1, right? Times now the reciprocal of a sub n, which was n squared plus 1 over 3x minus 4 to the what? N. Okay. Any questions? We're good? Cancellation that we get here is pretty nice. Well, it's actually not that nice. It's all right. It's just one thing, one factor. All right. Now what I'll do is I'll keep my absolute value. I'm going to put all my n stuff in one absolute value. So my n, I have an n squared plus 1. And down here, I've got this. Those two I'll put together. That's n squared plus 1 over, n plus 1 squared plus 1. I'm going to go ahead and, is it all right if I multiply that out? Okay, what would you get if you did n plus 1 squared plus 1? Plus 2, okay? And then in absolute values, the the stuff with the x in it. So that's what, 3x minus 4? Any questions on that? Now, when we take our limit now, the n is here, right? So n, we have polynomial, we have the same power. You could do L'Hopital rule, or you could divide everything by n squared on top, bottom. What's going to be? 1. Okay, so that limit's going to be 1. So this is going to be going to 1 times what? 3x minus 4, which is not affected at all, right? And so our answer is basically absolute value of 3x minus 4. But for convergence and ratio tests, we need that to be less than 1. We need the absolute value of 3x minus 4 to be less than 1 for convergence. Yeah, so now we'll use what I said earlier, right, at the very beginning of class. All right, next page. I've got absolute value of 3x minus 4 is less than 1 is the same as saying negative 1 is less than 3x minus 4, which is less than 1.
When you put them in between, you take out the absolute value?
Yes. And this is just inequalities, so you can treat these like you would any other inequality. Let's try and get x by itself. So how about we add 4 to everything? We add 4, here, here, and here. We get a new inequality, 3 less than 3x less than 5, right? And then finally, divide everything by 3. Now, what is the one thing we have to be careful with when we divide? Negatives. We flip signs, but here we don't have any. So we're going to divide, we're dividing by 3. It's not a negative number. So we get 1 less than x less than 5/3. So this is it right here. That means that this power series does not always converge like the one we had before. It only converges if I pick a value, an x value, that's between 1 and 5/3. Anything outside of that, it's going to diverge. Questions? Yes. I knew someone was going to ask me that. We have to address that still. What happens at 1? What happens at 5/3? To answer your question in short, we have to check 1 and 5/3 separately. They may do the same thing at 1 and 5/3. So it may converge at 1 and converge at 5/3. It may converge at 1 and diverge at 5/3, or may diverge at both. We have to actually check them both. But that'll be after our next note. Okay, so I think we do one more example. I might skip that example. We'll see. All right, so here was that problem we just did. Okay, so same sort of thing. I have it set up here. Let's pick an x value. Let's pick an x value between 1 and 5/3. So I picked 1.1, right? I picked my x value, and now I'm going to start making terms of the sequence increase, and watch what happens to my nth partial sum. It should do what? It should converge. So I'm going to start grabbing these. Just keep an eye on that nth partial sum. That's it. It looks like it's not changing anymore. So I'm already getting that convergence, you see? But now let me draw it back. And now let me pick something outside of our interval of convergence. So 5/3, what's bigger than 5/3? 2? 2. So look at my nth partial sum. What is it? Right now, 2.6. As I start adding terms, goodbye. There it goes. It's taken off. See it? All that's happening now is I'm adding more and more, just getting huge. It's diverging. All right, so if you look at that power series we just did, if you look at the original power series, right here, this in black, we could call this a function, right? We could define that as a function, but its domain would be what? Everything between 1 and 5/3. So if we restrict the x values to that domain, that interval, this is a well-defined function. If we go outside of that, this is not well-defined because it becomes infinite. So you can't define a function to be infinity. Here's the, f of x equals infinity. Doesn't make any sense. Yes? What's that? Mm-hmm. Mm-hmm. Yes. Okay, so the idea behind a function is that you have an input, right, and you have an output. If I plug in something between 1 and 5/3, I have an input, and then I plug that through this function, and it's an infinite series, right? It adds up an infinite number of terms, but that infinite number of terms converges to a single number. That's my output. What this sums to is my output. And it's a number, right? So the input, if we go back to that visual I had here, when I change that x value to 1.1, there, that'll work too, 1.04. And here's my, wow, that converged way too fast. Let me make it 1.2. There we go. That might have converged already too. So if I plug in 1.2 into this function, it's within its domain, right, that we were saying, then it should spit a number out. This function should. Now, the number it's spitting out is, well, it's not that. It's not that. Well, okay. I'm not even going to say it's this because this is it to, 1, 2, 3, 4, 5, 6 decimal places. I just told the computer stop here. I could have had the computer keep going. But the more terms I go, I get closer to the actual number. But it is a single, unique, real number. So one input, one output. You can't see, the thing is we can't add forever, right? So in real life, what we do is we only go out as far with this power series as we need to achieve the desired accuracy for whatever it is we're trying to do. Right? We talked about that a little bit last class. If you're building an aircraft, your tolerances need to be very tight as opposed to building a workbench. You don't need your legs to be within 1/1000th of an inch. So whatever it is, that's how far you go out. All right? Okay. The next example, I'm going off our sheet again here, is this Bessel function, which I'm considering skipping only because of time. Maybe offering that as a take-home. No, because I did it on my other video. Never mind, I can't do that. Everyone's like, yes. Okay, so I did that Bessel function on my other video, right? That I had y'all watch. I did. So I'm not going to do it again here in class. I was going to do it, but I don't think I will. All right, so just watch my other video. It's the same thing, ratio test. I actually went to Wolfram and found an example of how you can use Bessel functions along with some cosine and sine to model like a drum, like what do they call the thing on the drum? The thing you put on the drum head, the rubber thing or whatever it's made out of. What do they call that? Skin or the membrane, right? Whatever that is. Like if you hit it with a, what do you call the thing you hit it with? See, I'm not in music. You hit it with a stick, right? You hit this skin with a stick. So you hit it, and that's what it does. The wave pattern on that membrane can be modeled with Bessel functions along with sine and cosine functions. Yeah. So if you go to Wolfram Alpha or go to Wolfram.com, they have a demonstrations, and just type in Bessel, and there's one that you can watch where you can animate, just like you know how to do my animations in here, just like that where you can animate. It'll show the drum moving. It's pretty cool. But we're going to skip it. All right. I do have a bonus question involving Bessel that I'll send you home with. All right. Let's move on to the next example, though, here. I do have, well, that was the last one. We need to get to the theorem now. So let me get back to my notes here. All right, here's the theorem. Everyone on this page where it says theorem? Very important results here. Given a power series, okay, there's our power series, just a generic power series about A, that's what we said, power series about A. There are three possibilities for this series. First of all, it converges when X is A only. And we talked about if X was A, then you have a bunch of zeros and you just have that first C sub 0. And that converges to C sub 0. So this theorem says that it converges at only X is A, or it converges for all X, which we just saw a second ago, right? Or there is some number, capital R, such that if X minus A, the absolute value of that quantity is less than R, it converges. And if the absolute value of X minus A is greater than R, it diverges. So this is just saying that there's an interval where it converges. Those are the only three possibilities for a power series. That's it. It either converges only when X is A, always converges, or converges on some interval. And that interval is what we're going to call the interval of convergence. The capital R is what we call the radius of convergence. So keep in mind that this absolute value right here, right there, absolute value of X minus A less than R, that really means this. I got that from doing this right here. Okay, so you drop your absolute value, you put your capital R, negative capital R, then you add A to both, and you get this. Yes? So that will always be your interval of convergence. I didn't highlight it there, but that's a definition. Interval of convergence is this interval right here. Capital R is called your radius of convergence. When I was thinking about this the other day, I don't know why, I saw something, it was like, I was looking at these notes, and I was watching TV, and there was something on the Unabomber on one of these history channels. And I don't know a whole lot about the Unabomber, but he was a mathematician. Did you all know that? Yeah. And he was really into what are called boundary value problems, which is kind of what you were alluding to, like what happens at those endpoints. That's along the boundary of the interval. Now he wasn't, I'm saying that he was studying this. I'm just saying he was talking about functions, and functions just behave very strangely along their boundaries a lot of time of their domain. And so this interval of convergence, these two endpoints are going to be very important to us because they behave differently. It's not always the same. We know inside what happens, we don't know what happens outside. All right, so because of that, the endpoints of our interval have to be tested. And there's only a couple of possibilities we could have for convergence. This one would mean what? What do brackets mean on an interval? Include them, right? So we could get an interval and wind up that both endpoints give us convergence, which means it would be a closed interval. We could get these two possibilities where we have right endpoint included but not left. This would be left and not right. These are called half open intervals or half closed, however you want to look at it. And then over there, open interval. That means don't include the endpoints. So if we have our interval of convergence, it's going to be one of those four possibilities. But we'll have to check. So here are the examples I have for the rest of this class. Okay. Find the radius of convergence and interval of convergence of that. What's different about what I'm asking now is that we are still going to do ratio tests. We're still going to do all that. But at the end, we're going to need to know what capital R is, and we're going to need to know what the interval is. Yes. And the endpoints. These will always converge? I don't know. It'll depend. We're about to see. Yeah. Remember the three possibilities. Converges only if, in this case, only if x is what? Which would be for us 3. So this power series only is, you're going to do one of these three things. It's only going to converge when x is 3. It's only going to converge, or no, sorry, it's going to converge everywhere, or it's going to converge on some interval. Well, what we need to do is figure out which it is. So let's do ratio. I'm not going to write out the terms. Ratio test. Were y'all okay with how quickly I wrote out the last one, or was I skipping too much work? That's all right? Sure? All right. All right, here's what I get. Negative 1/4 to the n times negative 1/4 x minus 3 to the n times x minus 3 all over n plus 1 square root n plus 1. So that's a sub n plus 1. That's what I get when I plug n plus 1 into that sequence. Then times the reciprocal of a sub n. Sorry, I didn't let y'all know the gentleman sitting in the corner. Did y'all see him? Anyone know who that is? I've never seen him before. No, I'm just kidding. I'm just kidding. He's a chair of the math department, the intern. So we have faculty evaluations every 2 years. So this was mine. Did it seem pretty normal? I was trying not to make it seem like exceptional. Was it normal? Okay. You sure? Are you just saying that? I mean, it's hard because we have to know they're coming. So it's, it's kind of like, they're coming, but you don't want to make it like so different that your class is like, what the hell's up today? Who's this guy? Where's he been all semester? You know what I'm saying? I think that's kind of shady because a lot of instructors do that. Like they teach a certain style and then that one day they're like, we have a classroom activities and it's like, cartwheels and shit, and it's just not, it's not realistic, So I'm trying to stay within what I'm normally doing here. Okay, but that's what it was. All right, getting back to this. Cancel out that negative 1/4 to the n. Cancel out that x minus 3 to the n. Anything else? Cancel? Nope. Okay, so let me gather all my n's together. I have the n square root n over n plus 1 square root n plus 1 times, what did we have there? Absolute value, negative 1/4 times x minus 3. Is that all right if I write it that way, like that?
You can write it as a positive, right?
I will on the next step. Yeah. Where? Well, it'll come out as a positive 1/4 though, because that absolute value. That's where the absolute value is so important now, because the absolute value is going to make that a positive 1/4. But we'll take care of that in a second. Let's figure out what's going on with this limit. 1? How? Just sounds good? The same powers? You could do it almost like separately, right? What does this do? That's n over n plus 1, right? Infinity over infinity, L'Hopital's rule, 1 over 1, done. And then on this one, you could almost look at it like, use this property that when you have square roots, top and bottom, you can put it into one root, right? And now what's that? Inside that root, what's that? 1 square root of 1 is 1. So you really have like a 1 times 1 there, don't you? That's just one way you could do it. 3 halves. You could also convert it over to 3 halves. So in any event, you need to determine that that's a 1. Well, you can, but if it's wrong, I'd be feeling for you, you know. I saw that a lot on the last test. A lot of students on the last test using comparison test assumed A sub n was less than B sub n, but never really showed it and convinced themselves or me that it was true. Or, no, I didn't point this out, but one of the biggest mistakes on the test was using comparison test when A sub n was not greater than 0. If you go back to comparison test, if you're going to compare two sequences, you have to have that they were both positive. And a lot of people were using the comparison test, and A sub n wasn't always positive. Talking about that one, I think it was sine n over n. Okay, we can talk about that. If you want to talk about tests, we can do that separately. Okay, so we have a 1 up in front of that, and then we have what, 1/4. I'm going to drop the absolute value. 1/4 is going to take the absolute value of negative 1/4. 1/4 is from taking the absolute value of negative 1/4. And then I still have the absolute value of x minus 3. That I cannot change, because I don't know what x is. So the absolute value can only take the negative off the 1/4. That's where I am. I'm there. That's it. Questions?
So like whenever you have an absolute value, right?
Mm-hmm.
And you have a variable and a number with a negative,
You don't mess with that. That's right. Whatever's in that parentheses is going to be in your absolute value. Now we need this right here, the whole thing, right, to be less than 1 for ratio test, right, to work. Which means that we now need to multiply both sides by 4. Not yet. We need the absolute value by itself first. Okay, what I've done is I've isolated the absolute value. So if you kind of squint your eyes, what we have is this. We have absolute value x minus a is less than capital R. Do you see it? But it's only when you get this over here to the other side, you just get the absolute value by itself, that you have your capital R. So what is your radius of convergence? 4. Now think of radius of convergence as this. If I say, hey, I have a circle with radius 4, right? Then if you're standing in the center, it's 4 this way, 4 that way, right? 4 in any direction. Our interval has a radius of convergence of 4. So that means that if I'm on a number line, whatever this is, the middle, it's 4 each direction. So it's 4 this way and 4 this way, which we're about to see when we solve this inequality. But it's kind of like a radius, but it's not a 2-dimensional circle. It's the radius on a number line. It's kind of weird, but that's the way it is. It has to do with the fact that later on your domain is in 2 dimensions. So your domain is like an x and a y, so you do have a circle. And you have a radius of convergence because your domain's a circle. What now? Take this. Yep. Change it. Negative 4 less than x minus 3 less than 4. Add 3. Negative 1 less than x less than 7. That's our interval of convergence. I'll call it interval convergence right there. And R was what? 4. I'll put that over here. I'll box that. Well, hold on. Don't box that interval convergence. I'm sorry. We haven't checked our endpoints, right? So far, though, this is what we've got. I'm going to just draw this on a number line so we can see what we've got. We know that if you have -1 and 7, what's right in the middle of -1 and 7? 4 is in the middle, right? Is it 4? It's 3. Thank you. 4 in each direction, right? If I go 4 this way, it's 7. If I go 4 that way, it's -1. Do you see radius of convergence is 4? 4 in each direction, so in the middle is 3. Isn't A 3? Right? So let me see if I can really get you to get your head around this. With the power series, what were the 3 possibilities? It only converges when x is A, or, okay, give me the third one next though. Only at A, or on some interval, including A, or everything. Those are the 3 possibilities. Do you see it on a number line, how that really is working? It's either a single point, some interval including that, or everything. Now, what we need to figure out is what that interval, if we're including the -1 and the 7. So here's how we have to look at it. If, let's start with -1. If x equals -1, what does our power series become? So I'm going to go back to the original power series. I'm going to rewrite the whole damn thing. But I'm going to replace my x with what? -1. So there's a -1 minus 3 to the n all over n root n. Does everyone see I've replaced the x in the power series with -1? That means I don't have an x anymore, right? This means like a power series from your test, like the exam you just took. Let's see what happens here. This is n equals 1 to infinity. We have -1/4 to the n, but then -1 minus 3 is what? -4 to the n, all over n root n. Now, what would happen if I put those two together? You write these are both to the n power. So can't I put them together and make them both something to the n? What would they be if I put them together? Positive or negative? Positive 1 to the n over n root n. Questions on that? That was -1/4 times -4. Positive 1. And that's just the same as sum n equals 1 to infinity. 1 to the n is 1, right? And then over n, what is n root n? Isn't that n to the 3/2? That's a p-series. Isn't that a p-series? This is a p-series. P is 3/2, which is bigger than 1, which means what? Therefore, I'm going to say it this way. Our series converges when x equals -1. So on that interval I had drawn earlier, right, -1 to 7, at -1 it does converge, right? Now we have to figure out what happens at 7. Any questions, though? This is a lot of work you have to do for these because, I mean, you have to do a ratio test, figure all that out first, then that'll give you your interval. Then at each endpoint you have to do a separate test, which might turn out to be p-series. Who knows what it's going to be? So let's do if x is 1. Or sorry, if x is what? 7. Our series is sum n equals 1 to infinity, -1/4 to the n, 7 minus 3 to the n, all over n root n. So this is sum n equals 1 to infinity. Yeah, it's, look at, I've got negative 1/4 to the n, but this time times 4 to the n, not negative 4. Everyone see the difference there? We have a positive 4 here instead of a negative. And that means when I put it together with the negative 1/4, it's negative 1 to the n over n root n. And that is an alternating series. So we have some options, right? You could take the absolute value of it. Yeah. But didn't we have, if the absolute value of a series converges, the original one converges? Right? Theorem 8. You could also do alternating series test here. But I think Theorem 8.4 is even better. Theorem 8.4 says if the absolute value converges, then that converges, right? And we already know what happens to the absolute value of that, don't we? Right? The absolute value of negative 1 to the n over n root n is exactly the same as 1 over n root n, which converges. Right? Because it's p-series. Yes? All right. So what is our interval of convergence then? We're ready for our final answer. Therefore, the interval of convergence is negative 1 less than equal to x less than equal to 7. Or if you like, you could put negative 1 to 7 brackets on both. Either one of these is good. Yes. That's right. Every power series converges at A. The question is it only A? Is it some interval including A, or is it everything? All righty. How do y'all feel about this? Yes. Interval of convergence. What's our next one here? Yeah. Let's do this one. You ready? This one's going to be interesting. Why did I take this one off here? You have n squared x to the n over 2 times 4 times 6 dot 2n? Yes? Okay, let's do that one. So we have sum n equals 1 to infinity n squared x to the n over 2 times 4 times 6 times dot times 2n. I put one like this on here because some of you had trouble with that on the test. Do you want to write out the first few terms or not? You think you could do that pretty easily? Yeah? You're okay with that or not? All right, let's go to ratio then. Ratio test. So if we do the ratio test here, limit n goes to infinity, it'll be n plus 1 squared, x to the n x, all over. Now this is where I think a lot of people had trouble. This would be 2 times 4 times 6 times dot, 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 all the way out to what? 2 times n plus 1, right? Which, watch the way I'm going to write this. 2n is the one right before it. 2n plus 1 is the one right after it, right? If this is 2 times n plus 1, the one right before it would be 2 times n, because it's one less than this, right? Now, I didn't distribute, I will. But in class last time, I think what I was doing is I was just writing that last one as 2n plus 2. And people were losing sight of the fact that the one right in front of it was 2n. 2 less than that, right? Take 2 away from this, you're back here. Take 2 away, because every one of these is 2 less, 2 more than the one in front of it. So either way, this or this. Questions on that? What am I missing? Absolute value. Okay. Times over here, what do we have? Reciprocal, so 2 times 4 times 6 times dot, 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 all the way out to 2n over n squared x to the n. And now we get some canceling here. X to the n. What else cancels? Yeah, my 2's cancel, my 4's cancel, my 6's cancel, everything all the way up to what? 2n. You see why I included it in this one? I included it so you could see it cancels, but the one next to it doesn't. So the only thing left is an n plus 1 squared on top, an x on top, what's on the bottom there? 2n plus 2 and an n squared. So this limit, as n goes to infinity, I'll put all my n's together. I have n plus 1 squared over n squared times 2n plus 2. That okay? And what about my x? Absolute value of x? Yeah, this right here, because it's a squared over something that's cubed, you do enough, divide through by n cubed or L'Hopital a couple of times, you're going to get 0. Yes. Just go, yeah, that's fine. Yeah, that's okay. So this equals 0 times absolute value of x, which is always less than 1, right? For all x. No matter what my x is, it's always going to be less than 1. Which means what? R is what, and what's my interval of convergence? R is your radius, so it's infinite. Right? You have an infinite radius, just infinity. Your radius is how far in each direction? Infinity that way and infinity that way. What's the interval? Negative infinity. You can say less than x, less than infinity, or if you want, you could say negative infinity to infinity. But remember, don't put brackets on infinity. So we don't have to test endpoints, right? Because you don't have endpoints. Infinity, right? So of the 3 possibilities, we've seen 2, right? We've seen an interval, we've seen everything, but we haven't seen just one thing. So let's look at the next example. Find the radius of convergence and the interval of convergence of n equals 1 to infinity of n factorial times x minus 3 to the n. ratio test. Limit n goes to infinity, absolute value, n plus 1 times n factorial, x minus 3 to the n, x minus 3, all over what? See, there is no fraction here, so it's just going to be a sub n plus 1 over a sub n factorial, x minus 3 to the n. We get there, there. Does anyone have any questions where I got any of that? Absolute value. What's the only things left are what? N plus 1 and x minus 3. So I'm going to put the n plus 1 in its own parentheses and the x minus 3 in its own. Uh-oh. What's happening as n goes to infinity here? This thing's going to go to infinity times x minus 3. We need that to be what? Less than 1? There's only one way that's going to happen. If x is 3. If x is 3, this is 0. Not approaching 0. It is 0, right? And so what we have is something that's getting big times 0, which is different than something getting big times something getting small. That would be an indeterminate form. Do you see the difference? There's a huge difference in that. If you let x be 3, this is the number 0, times a number that is getting huge. That's 0. So the only way it's going to happen, if x equals 3, right? If x equals 3, the series converges. Do you have any questions on that? So I've basically shown you an example of the 3 possibilities. This one was a possibility where there is no interval of convergence. It only converges if x is 3, which basically made all those, a bunch of zeros out there, except that first term, right? And then I've shown you an example where we have the interval, where we had to check endpoints, or test endpoints, and I showed you where infinity is the interval. The hardest of all of those is the one where you have to check the endpoints, because that's a ratio test, and then 2 more tests. And that's the ones you usually see on a test, right? The ones that you have to show me the most. But that's not to say these won't show up. All right, do you get the idea behind the power series? We have, oh yeah, thank you. I'm glad you mentioned that. Radius, I didn't put it up here. The radius would be 0. The reason why is because when you're saying, okay, it converges where? At 3. So I'm standing on number line at 3. How far to the left and to the right can I go? Nowhere. There is no radius. A single point has there's no thickness, no interval. A single point has no width to it, right? So interval is 0, or radius is 0. Thank you for reminding me to put that there. All righty. We have 20 minutes. That's enough time for the quiz. I want to show you one thing, though. I'll try and stay under 2 minutes here. We have all seen the unit circle, right? Circle, right, from pre-cal. It's basically all the points. And let's actually look at it, instead of a circle, let's look at it as a disk. It would be all the points that are within 1 unit of the origin, right? If I start at the origin and go out, anywhere in here, it's solid, right? Solid. You would have anything that's within the distance between the origin and the end is 1 or less. It's called the unit disk. Yes? This is in 2-dimensional space. That's how we write 2-dimensional space, R2. 2-dimensional. Now, we have a more general name for this. We call it the unit ball. Okay, the unit ball in R2. So this is what the unit ball looks like in R2. It's a disk with the radius 1. What do you think the unit ball in R3 looks like? Three-dimensional sphere, right? It's a sphere. Solid ball. Okay? And basically everything is, radius of this sphere is 1. What do you think the unit ball in R1 looks like? Okay? So here's the number line, R1. Here's 0. -1, 1, right? Everything in there, including the endpoints. So the unit ball in R1 is the interval between -1 and 1, including -1 and 1. The unit ball in R2 is a solid disk, radius 1. The unit ball in R3 is a solid ball in R3, right? Radius 1. The unit ball in R4, unit ball in R5. There's actually, so the concept is always the same. In the space, the unit ball is all points that the distance from that point to the origin is less than or equal to 1. So you go draw a disk. Every point that you pick back on this disk, right? If I pick a point here, that point has the coordinates x, y. Then what I can tell you is that the distance is less than 1. That means, how do we find distance? It's the square root of, it'd be x squared plus y squared. That would be the distance from that. That would be the distance from here to here. You just do Pythagorean on a triangle here. That right there would be less than or equal to 1. In 3-dimensional space, guess what it is? It's x squared plus y squared plus z squared. Square root has to be less than or equal to 1. Guess what it is in 4-dimensional space? X squared plus y squared plus z squared plus your 4th variable, k squared, square root less than or equal to 1. 5 space, 6 space, 7 space. And there's even an infinite dimensional space. There's an R infinity. I don't know, when we were talking about interval, and we started talking about, why they call it the radius of convergence. Radius, when it's kind of weird to talk about radius on a number line, but it's because this extends out into 2-dimensional, 3-dimensional, and on. So radius makes more sense there, right? All right, now your quiz. All right, so let's do this. How can we do this? I'm debating right now whether to make you do it on your own or not. So yeah, let's see what you can do. All right, on this. And what I'll do is I'll let you use your notes from today. All right. You can, so it's open note quiz. Just don't talk to each other and don't look at what your neighbor's doing. I'll consider this like a test, but you're allowed to use your notes. This is covering what we just went over. So let's see how much of this will stick. I'm sorry? Just the notes, no book. Stop fighting over your quizzes. There you go. All right, enjoy. You have 17 minutes.